Okay, so in this class, we are going to continue to do something about damping oscillation of the mechanical system. So we are going to continue to do the solution with damping. So that means C is non-zero. Okay, C is non-zero. We get three cases. They are underdamp, overdamp, and critical damp, right? So we get three cases. And the solution looks complicated, but we want to draw the graph and see what's the meaning of those three cases. So firstly, let's take a look at underdamp. Underdamp means there are two complex solutions. So let's see. For the underdamp, that means two complex solution. And in the last class, we did case A. So you can see here, where's our solution? Solution is given y equals e to something times c1 cosine mu t plus c2 sine mu t. And we can do the same thing if we do the right triangle, like a c1, c2, and we can get A, right? So same procedure. Let's see our solution. We simplify our solution. Okay, solution come from original solution should be this one, mu t plus c2 sine mu t, and after we simplify, it's going to be a times e to the, so e to the this thing still keep in front, and we just combine those two terms, okay, and it becomes a times cosine mu t minus v. So this is the solution, and you can take a look at this solution if we draw the graph. At the beginning of class, we did a no damp. No damp means there is no this term, so our oscillation is going to be from negative A to A like this, right? But here, our solution has e to something, and we know exponential function, and e to the negative power is decreasing. So if we draw e to the x looks like this, and e to the negative x looks like that, decreasing, right? So actually this one, when t goes, e to the negative c over 2m times t is decreasing, so amplitude is decreasing. So our graph will look like something like this way. If I draw a little bit better, so something like it's going to, the oscillation looks like this. Okay, this means underdamp. So it's like the spring, when we pull this down and release, and it will move up and down, oscillate, and at the end it will stop. Okay. Second case, under this is 2A, right? And the 2B and the 2C, they have the same graph. 2B means critical damp. That means what? That means we only have one real solution. Oh, we have one real solution repeated twice. I hope this can help you to remember. So two solutions. That means going to be like a e to the something and a c1 plus c2t, kind of like this kind of solution. Okay. And the 2c means overdamp. Overdamp means what? Two different real solutions. That's like a c1 e to the like we say at c2 e to the bt, something like that, the solution. Okay, and if we draw the graph will be given by this. Okay, So this is y and is going to get close to equilibrium position. That means when we release the spring, it's go back to the equilibrium position and stop there. Don't oscillate. O is maybe like past the equilibrium position and come back to the equilibrium position. So this is like y equals 0 equilibrium position. So for 2B, 2C, critical temp and over damp, they can pass equilibrium position at most one time. No oscillation. Okay, so just to remember those things. Under damp, there is oscillation. Critical damp and over damp, no oscillation. Now let's take a look at the example. So from the example, you can see this problem is not difficult. We can solve this easily. Let's see. Here we have a differential equation like this one. And y0, which is 2, y prime 0, which is given by 6. This is initial value problem. And you can see this differential equation actually has no damping, right? Because there's no y prime term. Okay, so that means C equals 0, no damping. That means no dash part. Okay, no damping force. And we want to solve this. It's pretty easy to solve. And we want to decide frequency, amplitude, phase, period of the motion. Okay, let's see how to solve it. First step, just solve differential equation regularly. R squared plus 9 equals 0. This is PR. And we get R equals plus minus 3I. Right, so we know how to write down the solution. Solution should be C1 cosine 3t, C2 sine 3t. And next, this is initial value problem. We can find the C1, C2 by using the initial conditions. So firstly, if we plug in y0, y0 should be what? C1, which is given by 2, right? y0 equals just C1. So our solution should be 2 cosine 3t, C2 sine 3t. And next, we're going to plug in y prime 0 equals 6, the initial condition, second initial condition. So definitely we need to calculate the derivative. This one should be negative 6 sine 3t, 3c2 cosine 3t, and we plug in 0. This should be 3c2, which is given by 6. So c2 also equals 2. Is that right? Okay. So what is our solution? 2 cosine 3t, c2, like c2 is also 2, 2 sine t. So this is the solution satisfy this initial condition. And next, we want to simplify because we want to find the amplitude, the phase, and omega. So definitely, sorry, here's 3t. So definitely we need to do this thing. We put C1 here and C2 there, right? And calculate A. What is A? From this one, it's easy to see. So it should be square root 4 plus 4, which is root of 8, and 2 root 2. So A equals, if we simplify, this should be 2 root 2, and the cosine, the same as before, omega t minus phi. And then what's the phi? Oh, phi. This angle here, you can see, should be, because those lines are the same thing, so it should be powerful, right? Powerful. Okay. So from here, we know what is A. 2 root 2 amplitude. And what is omega? Omega is the coefficient in from t, so it should be 3, right? And what is t? T should be 2 pi over omega. Is that correct? So what is frequency? Opposite reciprocal of period. Okay, so we got those two. And next, what is asking for? The phase. The phase is just powerful. Now let's try example 2. Okay, example 2, we have an initial value problem, but this system has damping. Let's see. 2y prime plus 5y equals 0. This is the oscillation system also. Like y0 equals 1, y prime 0, which is 3. Okay, so let's see. With the differential equation here, we can solve this using what we learned before, 8.2 and 8.1. So let's see. Firstly, we find the PR, r squared plus 2r plus 5. And we try to solve r from here, right? And we noticed we cannot factor this out, so we use the quadratic formula. 2a negative b plus minus b squared minus 4ac. Okay, we noticed that we will have a complex solution, so which is negative 16 over 2. Simplify, negative 1. Okay, so let's continue to simplify. 4i here and divide by 2 again. So negative 1 plus minus 2i. So we get two complex solutions. In this case, our solution should be what? Let's see. Y should be C1 e to the a t, right? And cosine 2t, okay? And plus C2 e to the negative t sine 2t. Or you can factor e to the negative t out. C1 cosine 2t plus C2 sine 2t. So this is our solution. Next, we want to use the initial condition to find C1, C2, same as before. So y0 equals to, plug in, so it should be C1, and which is given by 1. So C1 is 1. So our solution should be e to the negative t cosine 2t plus C2 sine 2t. Next, we find the derivative of this function. So it should be negative e to the negative t cosine 2t plus C2 sine 2t f prime g plus f g prime. So negative 2 sine 2t to C2 cosine 2t. Is that correct? So next, plug in the initial condition y prime 0, which is given by 3. And then when we plug in, should be negative 1, because when we plug in here, right? And then when we plug in, they all become 0, sine becomes 0, sine becomes 0, and plus 2c2, which is given by 3. So we get c2 equals 4 divided by 2, which is 2. So our solution should be e to the negative t, c1 is 1, and c2 is 2. Okay, so this is totally same as before when we solve 8.1 and 8.2. Next, we want to combine those two sine cosine into one function. So it's kind of like c1 equals 1, c2 equals 2, and what here? A should be amplitude, right? Right triangle, so you can see root of 5, 1 plus 4. So for this one, we turn this into root 5 e to the negative t, and here cosine, and what is omega? Definitely 2t minus v. When we simplify or combine, then we know our amplitude is root 5. our omega is 2. So our t should be 2 pi over 2 should be pi, and frequency should be 1 over pi. If we know omega, we can know frequency and the period both, right? And the next thing, we need to find the phi. So what is phi? So phi, you can do any method. So phi here, I just use tangent. So because I know tangent of phi is 2 over 1, so my phi should be tangent inverse 2. So let's see. Frequency, period, amplitude. So we get all the information we want to know. And if we want to draw the graph of this one, this is underdamped t, here's yt, and here largest is root 5, here is negative root 5, and it's going to be like a phase like this. Okay, so this is our graph for this solution. Let's see. Yeah, that's all we need to know for this section, and you can try some other homework problems. From the example, you can see we don't need to memorize all the km anything. We just look at the specific differential equation and solve it and combine them, find what we need, like amplitude, period, frequency, those kind of things, right? So this will be in the final exam, and here is the summary for this section. For the section is called the free oscillation. It's called we do just the free oscillation system. Okay, and we set up the differential equation, and we solve the differential equation. So here we need to know how to find solutions for 1, no damping. That means C equals 0. So usually the differential equation looks like this kind of thing. Okay. Free oscillation means capital F equals 0. That means the right side is always 0, homogeneous. Second thing, we need to know with damping. And then we have 3 cases. Case 1, underdamped. Underdamped. Underdamped, our solution looks like this. Okay, so the solution will be 2 complex solutions, so e to the ax cosine sine, and combine them. Solution is going to be e to the a negative something t, and the cosine omega t minus phi, this kind of stuff. And the second and the third, critical and overdamped, they're the same thing, same graph. Okay, same graph. Pass through the equilibrium at most 1 time. And what's the solution? Solution for the critical should be e to the at, here like a c1 plus c2t, because second solution is t e to the at. One real solution repeat twice, and here 2 real solutions, c1 e to the a1t plus c2 e to the a2t, like this, overdamped, right? So based on the specific differential equation, we can just solve them. And we can stop here for this section.